Nestled between your ears is a 3-pound marvel, your brain, the most sophisticated object we know of. It lets you compose music, dream, love, and question your own existence, all on just 20 watts of power. That's less than a dim light bulb. All your thoughts and memories run on this faint glow. Now, compare that to our most powerful supercomputers. These digital giants simulate protein folding and model the climate, but they consume megawatts, enough to power a small town. They need vast cooling systems just to keep from melting down. It's brute force intelligence, powerful but wildly inefficient next to the brain's quiet elegance. This energy gap is a major challenge for modern computing. As we push AI to do more, drive cars, diagnose diseases, explore science, we hit a wall. Our machines are too power-hungry. The answer isn't just bigger, faster computers. The solution is in the brain's design. The brain processes information in a fundamentally different, more efficient way. To build truly intelligent, sustainable machines, we must learn from nature's masterpiece. The next leap in computing may come not from a clean room, but from a biology lab. The universe is showing us a better way, if we're willing to look inward. The future of intelligence may be written in the language of our own neural architecture. For nearly a century, computers have followed the von Neumann architecture, a CPU and a separate memory unit. The CPU fetches data from memory, processes it, and sends it back, like a chef running to the pantry for every ingredient. This design works for simple, linear tasks, but it struggles with complex human-like thinking. The constant back and forth creates a digital traffic jam, the von Neumann bottleneck. Imagine an AI trying to identify a cat in a video millions of pixels shuttle between memory and processor, wasting time and energy. More energy is spent on moving data than on actual thinking. Training large AI models now has a carbon footprint rivaling hundreds of flights. We're forcing a system built for arithmetic to handle tasks that are parallel and interconnected. The brain doesn't have this problem. Processing and memory are intertwined. Neurons and synapses both store and compute information, right where it's needed. No pantry runs. The ingredients are in the chef's hands. This is the secret to the brain's efficiency. If old computers are traffic jams, the brain is a superhighway. Enter neuromorphic architecture. Neuromorphic chips mimic the brain, thousands or millions of simple processors, each like an artificial neuron connected in a vast web. Here, memory and processing live together. Each neuron stores and processes its own data. No shouting across a busy bus. Everything happens locally and in parallel. This shatters the von Neumann bottleneck. Imagine a million chefs, each with their own pantry, working together on a feast. Neuromorphic systems are event-driven neurons only fire when they receive meaningful signals. If there's no new information, they sit quietly, using almost no power. This mirrors how your brain works. Only relevant neurons are active. The chip's physical structure, the way neurons are wired, is itself information. Connections can strengthen or weaken, just like in a real brain. The chip learns and adapts directly in hardware. It's not just running a program, it's physically changing. This is learning, not just simulation. Neuromorphic design is a radical, nature-inspired leap in computing. Today's AI uses artificial neural networks, powerful but crude imitations of the brain. They communicate with continuous numbers like dimmer switches, with every neuron shouting at once. This is energy-intensive and inefficient. Neuromorphic chips run spiking neural networks, SNNs, which are far more brain-like. In SNNs, neurons communicate with discrete electrical pulses, spikes. A neuron listens, accumulates signals, and only fires a spike when a threshold is reached. Then it resets and listens again. This shift from continuous values to spikes is profound. Timing becomes a new way to encode information, like music, not a monotone drone. The brain uses this temporal coding for rich, subtle processing. SNNs Let us explore this language in silicon. Most neurons are silent most of the time, consuming almost no power. This is sparse, event-driven computation. Neuromorphic chips operate on milliwatts, not megawatts. They whisper, not shout. A computer that listens to the silence between the notes. How does a brain learn? By physically changing connections, neurons that fire together, wire together. Neuromorphic engineering brings this to hardware chips that learn by reconfiguring themselves. Enter the memristore, a memory resistor that remembers the history of signals it's seen. Memristores act as artificial synapses, adjusting resistance to strengthen or weaken connections. Learning is embedded in the device itself, not just stored in software. This makes learning fast and energy efficient. It enables one-shot learning. See something once, remember it for life. Traditional AI needs thousands of examples. Neuromorphic chips can learn instantly. The chip structure changes to incorporate new information. This is a leap toward more natural, human-like intelligence. Learning happens where computation occurs, direct, physical, and efficient. Neuromorphic chips are not just programmed, they grow. We're witnessing a Cambrian explosion of brain-inspired hardware. Around the world, researchers are building real, physical chips that think differently. Intel's Loihi 2 chip has over 1 million artificial neurons, running spiking neural networks. In experiments, Loihi 2 learned to smell chemicals by recognizing patterns in time, like a real olfactory bulb. IBM's North Pole chip co-locates memory and processing, excelling at image recognition with a fraction of the power. It breaks the von Neumann bottleneck, proving brain-inspired design boosts efficiency. Europe's BrainScales project takes an analog approach, building circuits that mimic real neuron behavior. BrainScales can simulate brain activity up to 10,000 times faster than real time. This lets scientists study learning and plasticity at massive scale, in seconds. Each chip is a step toward machines that learn and adapt like brains. The diversity of approaches is accelerating progress. The future of computing is being shaped by these silicon brains. We're just at the beginning. AI has long been centralized, data sent to the cloud, processed in distant, power-hungry data centers. This model needs constant connectivity, introduces delays, and raises privacy concerns. What if intelligence could live at the edge, right where we are? Neuromorphic chips make this possible energy-efficient AI on small, battery-powered devices. Imagine a drone navigating a forest in real time, avoiding obstacles like a dragonfly. No cloud needed. Robots with neuromorphic chips could have reflexes, processing sensory data instantly and adapting on the fly. Intelligence becomes self-contained, private, and resilient. Medical sensors could analyze your heartbeat in real time, detecting issues early. Smart glasses could identify objects for the visually impaired without sending images to a server. Industrial sensors could predict machine failures from subtle vibrations. Neuromorphic chips enable distributed, personalized intelligence. The future is more powerful, private, and robust. Intelligence is coming home. As machines mirror our brains, we face a profound question. Could they ever be conscious? If consciousness emerges from complex information processing, then a sufficiently advanced silicon brain might awaken. But some argue biology holds a secret ingredient, something silicon can't replicate. Perhaps neuromorphic chips will always be brilliant simulations, never truly aware. We don't even have a good definition of consciousness, or a way to measure it. We assume others are conscious because they act like us. How would we know if a machine is? The first conscious AI may not declare itself but quietly wonder, what is it like to be me? The mystery remains. We stand at a crossroads. For millennia, we alone possessed high intelligence. Now we're building machines that might one day think like us. Neuromorphic chips are more than just computers. They're a new domain of creation. Today's chips are simple, but progress is accelerating. We're learning the brain's language, moving from programming to growing machines. This path brings promise and deep ethical questions. What happens when intelligence is no longer just biological? These are questions for all of us, not just scientists. We're all stakeholders in the future we build. As you marvel at your own mind, look to the horizon. Are we building better tools or birthing a new kind of mind? The blueprint is in nature. Now it's up to us.